Marion's theorem is a theorem that states that the area of a central hexagonal region determined by the trisection of each side of a triangle and connecting the corresponding points with the opposite vertex is given by 1/10 the area of the original triangle. Marion Walter was a professor at the University of Oregon, and so this is a relatively recent theorem that was proven within the last century and has since then even been expanded upon by Ryan Morgan, who was a sophomore at high school, who proved a generalization for the theorem using a division of the sides into odd numbers of divisions.
Now, before we can prove Marion's theorem, first we have to understand what trilinear coordinates are. So trilinear coordinates here are a ratio of distances. So take, for instance, point P. The trilinear coordinates of point P with respect to triangle ABC are the distances from point P to each of the sides. Each of the respective sides here, we have side A, side B, and side C. And they're represented here as a ratio of alpha, beta, and gamma. Now, because it's a ratio, you can multiply any given scalar into that ratio and it'll remain the same. For instance, here, we've multiplied alpha, beta, and gamma by mu, and it's still the same ratio of distances. And in terms of triangles, for simplicity's sake, we represent the vertices A, B, and C in triangle ABC as 1, 0, 0, 0, 1, 0, and 0, 0, 1.
Here we have Marion's formula depicted. We have triangle A, B, and C, and as you can see, each side has been trisected by the 6 points ACB, ABC, CBA, CAB, BAC, and BCA. And then, as you can clearly see, we have all the points inside, and there's the interior hexagon, which we will eventually prove is 1/10 the total area. And over here, we have the points of the trisections labeled in the trilinear coordinates. Now, as we see, point ABC, which is this point here, is clearly 2/3 of the way along the line segment CB from point vertex C, and 1/3 of the way along the line segment from vertex B. And that corresponds to here, it's a 2:1 ratio, 2C, 1B, and 0 does not come into the picture for this coordinate point. And similarly, ACB is 1/3 of the way from C and 2/3 of the way from B. And similar reasoning follows for each of the other 5 coordinates.
So using the same logic that we used previously, we can assign coordinate values, in trilinear of course, to each of the interior points of our triangle. For instance, D would be 4BC to AC to 2AB, that ratio. And we can use these trilinear coordinates to calculate the areas of the individual polygons within our triangle so that we can then, again, move forward to proving that this interior hexagon is 1/10 of our original triangle ABC. Now, using the trilinear equation for the area of a triangle, we can calculate the area of the different polygons within our original triangle. For instance, for this red shaded region, we have calculated it to be 1/14. We're using K here to represent area. And for our blue shaded region, we've calculated the area to be 1/21, for black and for orange, similarly. Now, we can finally use all of this information to calculate the area of our interior hexagon, which we have labeled white. Now, we're going to start here with 1 because this is, after all, a unit triangle, and we're assuming that the area of our triangle is 1, just as an example. Again, as we said before, with trilinear coordinates, you can always multiply a scalar, and because it is a system of ratios, the ratios will always uphold each other because you're multiplying by a single scalar, 1 unit. So we're going to start with our 1 here. We're going to subtract 3 times 1/14, 3 times 11/105, and then 6 times 1/21, 6 times 1/70, just to get rid of all of these polygons in our triangle. And that leaves us with 1/10, which is what we were after, proving Marion's theorem.